All right, let's get started. Okay, so a lot of you are still on snow day. Hope snow day went well for you. It's the first one in a long time. So we've got PS, whatever, 4. Is it PS4 here? What I'm going to do is give you an extra day on each of the problems because you weren't able to see the TAs yesterday. You have any problems or questions on the assignment or anything else? Yes. Okay. Okay, so he's asking about PS4-4. Basically, you've got this problem where you have containers of different sizes. You got to pour water back and forth until you get a certain amount of water in some of the containers. That's always been that shows up in a lot of IQ tests. So you're basically writing a program that could do something on an IQ test, or not writing a program, but designing a graph. And I'll give you the answer to the last question. The last question was, once you have the graph set up, what algorithm you need to do to solve the problem? The answer is breadth first search. Okay, because you want to make the graph so that what you're looking for is the shortest path between between vertices that have a couple of properties. So as you design the graph, you got to think about what does each vertex represent, and what does each edge represent in terms of the problem. And it's hard to say much more than that without solving it completely. But any other questions? Yes. No, if you can't do it. That's about the only information you get is whether an exception is thrown or not. So yes, rely heavily on catching exceptions. Okay. Anything else? Yeah. Mm-hmm. Well, so you're building a graph to represent the problem. And to solve the problem, you got to run some algorithm on the graph, which is breadth first search. That's what I said. So that's that. Okay, last time we were here. We were talking about, sort of taking a break from talking about graphs for a few minutes. We're going to talk about we're going to prove a theoretical result that says that the lower bound on comparison-based sorting is omega of n log n, meaning there will, no matter what algorithm you have that does sorting via comparisons and exchanges, no matter how clever you get, no matter how long you wait, you'll never find an algorithm that can do better than n log n in its worst case. Right? You can have the best case be better than n log n, but the worst case has to be n log n or worse. So this is a result that applies not just to algorithms with names, but to every algorithm that is known or is yet to be discovered. And the way we're going to do that is with decision trees. And to get you used to the idea of decision tree, we put up this decision tree, which shows you how insertion sort will behave, all the possible ways it can behave on when the input array is of length 3. So this is a decision tree for insertion sort on arrays of length 3. Now, what does this decision tree tell us? What can you look at it and read off from insertion sort? You can remember what this meant. Well, let's see what it's not. This doesn't tell us, this is not a recursion tree, right? first of all, insertion sort isn't recursive. So it's not showing you, it's not like insertion sort searches this tree. What does this tell us? Yeah. Okay. So he said the max number and min number of steps to do a sort, or another way to think about it is each branch in the tree is one possible set of comparisons, one possible sequence of comparisons that insertion sort will go through when sorting an array. So how many paths are there from root to leaf? In other words, how many leaves are there? 6. So if the idea is you start sorting the array A, B, C, so you can see up here in blue, you've got A, B, C. Now, for all we know at this point, the final answer, the final sorting might be A, B, C, it might be A, C, D, and so on. These are the 6 possible outcomes of the sort. Right now, insertion sort is just looking at that array. And the very first thing insertion sort will do is compare the first 2 elements. So do a comparison like that. And the answer will either be no or yes. Right? Insertion sort will get a definitive answer, so it'll go down, conceptually, it'll go down one of these branches. If it turns out B is less than A, what will insertion sort do to this blue array when it's working on it? If it finds out that B is less than A. Yeah, it'll swap B and A, that's what insertion sort does. And now insertion sort's in this state. It's looking at the array BAC. We happen to know that these are the only remaining possibilities. BCA and CBA are the only remaining possibilities for sorting the array. Why do we know that? We're taking a bird's eye view, but how can we know that? How we're able to rule out the other 3 possibilities? Yeah. Say again? Because we know B is less than A, and the other ones, which are on the left, require A to be less than or equal to B. So, yeah, we're here. And insertion sort just figured out what the second element of the array is, and so the next thing insertion sort does is it compares the third element to the second element. It compares C to B, C to A rather, and let's say C is less than A. So it will swap the A and the C, and will be down here at BCA. And then it's going to compare the second elements to the first element by asking is C less than B, and either way, the sort's going to be over. It's either going to do a swap and end or do nothing and end. So each branch corresponds to a particular way that the particular sequence of comparisons insertion sort may do or will do in a given circumstance. And which branch we go down depends on how the elements are initially ordered. What if A, B, and C are actually 1, 2, and 3? Which branch do we go down? Far left. We'll ask, is 2 less than 1? The answer is no. We'll ask, is 3 less than 2? The answer will be no, and we'll be done. Okay. What if the initially ABC is 3, 2, 1? Which branch do we go down? The far right. So in the first case, we do 2 comparisons. In the second case, we do 3 comparisons. But this just captures every possible thing. We're ignoring lots of things about the algorithm, like the index variables are being incremented and elements are being exchanged. We're just looking at the comparisons. So suppose now we looked at an array of length 4, A, B, C, D. Could we draw a decision tree for that? Yep, we could draw a decision tree. It'd still be a binary tree. What would its shape look like? Sure, similar to this one. What would be the shortest branch? Well, could we get by with just doing 2 comparisons to sort an array of length 4? No, in insertion sort, the quickest thing is arrays already sorted. So it would be, we would compare A, we'd find out that B is not less than A, and then we would find out C is not less than D, and then we find out D is not less than C, and we'd be done. So again, there'd be a branch where the answer is no every time, but it would be of length 4, or rather, there'd be 4 comparisons. 3 comparisons, I'm sorry. So of length 3 instead of length 2. Okay? And we tried to imagine what that tree would look like if we drew it for array of length 100 or 1,000. And again, in principle, it's possible. It'd get really tedious and it'd get really big. But you can predict what the tree would look like, right? What would be the length of the shortest branch if the array contained 100 elements? 99. That's just the best case for insertion sort. It'll do 99 comparisons and stop if everything's just right. On the other hand, there'd be a really long branch for the case where the array is reverse sorted. That'd be the worst case. Something close to 1/2 n squared. So it would be a very unbalanced tree. Right? Suppose we did this for merge sort. Suppose we were sorting A, B, C, D. What would be the first comparison merge sort would do? Okay, I heard a comparison of A to B and maybe something else. Why would it do A to B first? Say what? Nope, that's not how. Well, how does merge sort work? What would merge sort do with A, B, C, D? Yeah. Okay, so it would split A, B, C, D into A, B, and C, D. And then let's assume it does the recursion first on the first half. Someone else tell me what it does with the array A, B at that point. Yeah? It splits it up into an array A and array B, which is the base case for both. Then what happens? Then it merges the array A and the array B, which is going to require comparing A and B. So yes, the first comparison is A to B. What's the second comparison? C to D, which would be the merge on the other side of the recursion. And then, so it does those two first, and then it has to merge the array AB or BA, depending on how I got to order it in, the array CD or DC. And that'll be some more comparisons. So it's just, the decision tree just lets you read off what comparisons are done in what order, depending on, for each kind of input that's possible. All right, now, here's some questions. At least how many leaves do there have to be in a decision tree? Let's think about an array of length n. Well, actually, I'm not sure what answer I'm after here. 6. Okay. So how many leaves are there in the decision tree we just looked at? 6. Very good. Correspond to each possible ordering. Now, what if we had n elements? Yeah. In factorial, at least. Okay? And we say in factorial because there's going to be one leaf corresponding to each possible way that the array can be ordered when it's sorted. And there are in factorial ways to do that. How could there be more? It wouldn't happen with insertion sort, but how could it happen with some sorting algorithm to have more than in factorial leaves? Yeah. Right. It might. Let's just take the following example. Suppose that the first thing, we took insertion sort and we changed it. So the first thing it did was it just picked two elements, say the first element and the last element, and compared them. And then no matter what the answer was, it ignored the answer and went and did insertion sort the usual way. So suddenly, you've got this wasted comparison at the top, and then off the one branch, you've got the insertion sorts decision tree, and off the other side, you've got insertion sorts decision tree. And so each answer, there's two ways to get to it, depending on how that initial random comparison went. I'm not sure if my example quite works, but the idea is you could take an algorithm and have it just waste time doing comparisons and end up with more than one way to get to the same answer in the end. You can imagine that sort of thing. Okay, so you can end up with more than n factorial leaves, but you're guaranteed to have at least n factorial leaves. Yeah. Oh, you're saying if they're, yeah, okay. So if they're duplicates, then there are fewer than n factorial ways to order the, I mean, imagine they're all the same. Okay, you're right. There's only, if all the elements are the same, there's only one way to order, but there's still going to be n factorial leaves because the algorithm doesn't know at the outset that they're all the same. But to make this easier, let's assume all of the leaves are different. All the elements are different. So anyway, there has to be at least n factorial. And, for insertion sort, selection sort, and so on, they're going to be exactly in factorial leaves. So just, I think, anyway, it has to be at least in factorial. We saw the longest path in insertion sort was 3, and the shortest path was 2. And if we had an array with n elements for insertion sort, there'd be the longest path would be that roughly n squared over 2, and the shortest path would be n minus 1. And we just know that because we've studied insertion sort. We don't actually have to draw the tree to know that the longest path, the shortest path, is going to be n minus 1. That's just a aspect of insertion sort. Okay. Now, let's think about merge sort. What would be the shape of a decision tree for merge sort? We know for insertion sort, it's a binary tree. All decision trees are, but there's some branches that are short and some branches that are really long. So it's very imbalanced. Yes. Merge sort would be pretty equal. It's not exactly perfect, but it would be pretty close, very balanced. And of course, it'd be at least n factorial leaf nodes. What about quicksort? What would be the shape of the decision tree for quicksort? Would it look like merge sort's decision tree? Yeah. Right. It'd be more like insertion sort in that it'd be unbalanced. If you hit the worst case for insertion sort, boom, it's n squared. Okay? So it would be, if you cut off the really longest branches, it'd be pretty balanced, but it would still be, if you don't, it's going to be some extremely long branches because of that worst case. Okay, now, this is what I'll call God's algorithm. Imagine an algorithm, maybe it hasn't been discovered, but its decision tree has the algorithm has the absolutely best worst case. So the world's best algorithm that minimizes the number of comparisons required in the worst case. We don't know what algorithm that is, but what would the decision tree look like? What would be the shape of the decision tree for the world's best? Yeah. It'd be perfectly balanced or as close as you could get. Right? So it would be completely balanced. If there are like an odd number of elements, maybe there's a difference of 1 between some of the branches, but it'd be as balanced as you can get in a binary tree. Okay, so that would be a characteristic of the very best algorithm in terms of minimizing the worst case. And there'd still be those n factorial leaf nodes. All right, now, if you have a binary tree with n leaf nodes, what's its height? In other words, what's the length of the longest path from root to leaf? Log n, yeah. I say theta of log n because it's log n, give or take. Maybe it's -1 or just sort of depends on rounding. So if we took this balanced binary tree with n factorial leaf nodes, this decision tree for God's algorithm, what is its height? Yeah. We argued that it has n factorial leaf nodes. So it's going to be log of n factorial. So, I mean, if the height of a tree with n leaf nodes is log of n, the height of a tree with n factorial leaf nodes is going to be log of n factorial. So what bound does that put then on how fast the worst case can be of a comparison-based sorting algorithm? Yeah. Well, not log of n. Log of n factorial, right? That's how high, a balanced tree with n factorial leaf nodes is going to have a height of log of n factorial. So that becomes the lower bound on the worst case of any comparison-based sorting algorithm. You cannot contrive to have a better algorithm because its decision tree has to have at least n factorial leaf nodes, and so the best you're going to get is a height of log of n factorial. You can't get better. Yeah. Yeah. Okay, so when I said that the more balanced the tree, the better the algorithm, what I mean is the better the worst case of the algorithm. I'm not talking about the average case. And the worst case for merge sort is a lot better than the worst case for quicksort. All right, well, but what is log of n factorial? And so we've just shown that the worst case has to take at least log of n factorial time. And that's if the decision tree is perfectly balanced. If it's skewed at all, it's going to take more than that. So the question is, what is log of n factorial? And let's see what we can do. Here's one way to do it. Log of n factorial is log of the product of the numbers from 1 to n. And how can we simplify that? What property of logs can we use? Yeah. Right. The log of the product is equal to the sum of the logs. So we get that. So log of n factorial is log of 1 plus log of 2 all the way up to log of n. And I'm going to put an upper bound on this thing. So I'm going to say that sum right there, which is equal to log of n factorial, that sum is less than or equal to that. Okay? But how can I assert that? I mean to say if they're in log, we're adding log n to itself n times. So why is this sum here involving log n less than or equal to this sum here? Which, what's the argument? Yeah? Yeah. Yep. Log of n is greater than or equal to log of 1. Log of n is greater than or equal to log of 2, all the way down the line. And so that sum on the bottom has got to be greater than or equal to the sum on the top. But that sum at the bottom is just n log n. So what we've got now is the log of n factorial is less than or equal to n log n. Okay? So keep that in mind. You see a factorial, you think, oh, that's growing really fast, but we're taking the log of it. So let's do another way. Log of n factorial is equal to that same sum. Now I'm going to make it greater than or equal to something. I'm going to make it greater than or equal to log of n over 2 plus log of n over 2 done n over 2 times. Okay, where does that come from? So this top sum here contains n terms, log of 1, log of 2, log of 3, up to log of n being added together. This one has log of n over 2 plus log of n over 2 plus log of n over 2 done n over 2 times. In other words, this bottom one is n over 2 times log of n over 2. So how do I know, how does this greater than or equal to hold? Why is this sum greater than or equal to that sum? Yeah? Properties of what? You can make the argument that's similar to the argument up here with the summing the n log n's. Put the terms in this sum, the log of 1 through log of n, into correspondence with the terms in the second sum. What do you get? Yeah. Yep. We can do that, but I want to actually argue that this greater than or equal to holds before I do the simplification. So let's line up the final log of n over 2 with this log of n. Do you agree that log of n is greater than or equal to log of n over 2? Okay, what about log of n minus 1? Is that greater than or equal to the next log of n over 2? And we're going to go backwards in this top sum until we get to log of n over 2, which is going to be greater than or equal to that log of n over 2. So if you look at just the terms in the second half of the upper summation, throw away the first half of this first sum. It's easy to see that what's left of that first sum is greater than or equal to all of the second sum, because every term in the first sum is greater than or equal to log n is greater than or equal to log of n over 2. Plus, you got these terms that we ignored at the beginning. So just line them up one by one, write justify things, and you find out it's easy to see that the top sum is greater than or equal to the bottom sum, which is just n over 2 log n over 2, which is n over 2. I'm just doing some log simplifications here. But we basically find out that log of n factorial is bounded above by an n log n function, and it's bounded below by an n log n function. So it's theta of n log n. So logarithm factorial grows at the same rate as n log n. And for our sorting, it means that the lower bound for the worst case of comparison-based sorting is n log n. You can't do better. You can't find something that'll work in linear time if all you do are comparisons. And the thing to keep in mind is this is not a proof about a specific algorithm. It's a proof about any algorithm that works by comparing elements and exchanging them. And the way it takes advantage, the way it works is it's able to, we can argue about a decision tree. Every such algorithm has to have a decision tree. And so we can make arguments about it. Right? So there are degrees of difficulty in algorithms. There is, coming up with an algorithm. There's proving the complexity of an algorithm. You're putting an upper bound or a lower bound on the running time of an algorithm. But this is sort of the next level, making an argument about all algorithms for some problem. Can be tricky, but this is an example of one. So, are there any questions I could answer about this? Yeah. You're having a hard time seeing. Yeah. Okay. How do I know that n factorial is O of n log n? Because it's less than or equal to n log n. So we know, we showed right here that n log n or I should say log of n factorial is less than or equal to n log n. So if we graphed them, n log n would be above log of n factorial. So that makes log of n factorial O of n log n. It's called the curve is above the O. And the other way is we know that n of log of n factorial is greater than or equal to n over 2 log n minus n over 2 log 2. So if we ignore the leading constants, lower terms, you get the lower bound of log of n factorial. So we found one function that is above, and the second answer is another function that's below log of n factorial. They're both n log n curves with different constants. So the answer, if you graphed it, it'd jump right out at you. Yes. Okay, let's think about that. What if I said the worst case lower bound we can put on all comparison-based sorts is omega of n log n? What would I be saying? Yeah. Well, when I say omega, I'm saying the worst case would never be better than n log n. If I said theta, what would I be saying? Right. I would be claiming that the worst case for any comparison-based sorting algorithm is n log n. Okay, and that's patently wrong. The worst case of insertion sort is not n log n, it's n squared. Same thing for quick sort. All I can do is put a lower bound because I'm talking about all algorithms. They can certainly do worse than n log n. They can't do better. So that's why I put a lower bound. Yeah.
So this is all comparison based on.
Right.
So we put an O of n log n. That's also the best of best case.
Well, we proved it for the worst case. We put a lower bound on the worst case of every algorithm. These are all
worst case.
Right. Our final answer at the bottom of the slide there is the lower bound on the complexity of the worst case for any comparison-based sorting algorithm.
But the O of n log n is on the best of.
Well, the O of n log n that's on the slide is an upper bound on log of n factorial. That was just how I was just showing that log of n factorial grew as the same rate as n log n. Now, you can also say that comparison. So when we say comparison-based sorting is omega of n log n, we're putting a lower bound in the worst case of any algorithm. What's it mean when I say that comparison-based sorting is O of n log n? When I make that statement, what am I saying? I'm saying something different. Yeah. Well, I'm not saying there's no algorithm worse than n log n, because there certainly is. Insertion sort, for example. Yeah. No, it's not. You won't get the right answer by making it the reverse of what I'm saying about the lower bound on the worst case. It just means something different. Yeah. Yes. So when I say that comparison-based sorting is O of n log n, I'm saying there is a comparison-based sorting algorithm that runs in n log n times in every case. What is the proof? What's the proof statement like that? Yeah, you just have to find an algorithm that's O of n log n. So, right. Or you could just say the worst case. That's the same thing. Okay. So when you say that that a class of algorithms is O of n log n, you're saying that there's at least one that has that behavior. Oh, but when we say that okay, no, we can't say insertion sort is O of n, because it has to apply to all the cases, particularly the worst case. Yeah. Yeah. When you're saying that sorting is O of n log n, you're saying something about the worst case of some algorithm. When you say it's omega of n log n, you're saying something about the worst case of every algorithm. So they're not symmetrical. It's just the way the notation is used. Yes. Is what? I'm not sure if I've seen. I see where you're coming from. I'm just not certain I've seen that used that way in practice. All right. Now, suppose I ask you on an exam, what is the length of the longest path in the decision tree of merge sort when given 4 elements to sort? What would be the right way and the wrong way to answer a question like that? I've seen students try to answer that, not in an exam, but how would you go about answering that question? Right. So what students often do if I ask that question is they draw a tree. They try to draw the decision tree for merge sort for 4 elements, which gets kind of involved. You saw the one for 3 element insertion sort, and that's bad enough. So they'll draw the tree and then try to find the longest path in it or the shortest path, depending on what I ask. But if you know what a decision tree is, there's no need to draw it. If you want to know what's the longest path or the shortest path, let's say the shortest path in a decision tree for merge sort for 4 elements, what am I asking? Yeah. Yeah, how many comparisons are done in the best case of merge sort? It's a lot easier to just to think about, okay, if it's already sorted, how many comparisons will it do, than it is to try to draw a decision tree. So, on the other hand, if I ask you what's the shortest path in the decision tree for insertion sort with 1,000 elements, I don't think you'd be tempted to draw the tree. You would you'd think, oh, that can't be what I'm supposed to do, and you'd realize, oh yeah, I just need to think about insertion sort. All right, now we're going to move back to graphs. Okay, we're going to talk for a while now about strongly connected components. So we talked about connected components when we talked about undirected graphs. And that was just a clump. They're all hooked together by edges. It gets more subtle with directed edges. And so a strongly connected component, we're going to say that 2 vertices u and v are connected if there's a path from one to the other and vice versa. So in this graph up here, are D and B connected. No. You can get from B to D, but not vice versa. What about H and J? Yeah, they're connected because you can go H, K, L, J, so you can get that way, and you can go J, I, G, H. You can go the other way. You get from one to the other, yeah. Well, the term connected works either way. In an undirected graph, connected just means there's a path from one to the other, because you can get from one to the other, you can get back. But strongly connected is a term we just use for directed graphs. All right, so we know what it means for two vertices to be connected. Now, what we're going to say now is find the largest possible chunks of a directed graph such that every vertex in the chunk is connected to every other vertex in a chunk. And that largest possible chunk is called a strongly connected component. So what is a strongly connected component that contains the vertex D? All right, it contains D. Can you put any other vertices in with D and have them all be connected to each other? No, because it's a sink. So that won't work. What is a strongly connected component that contains the vertex K? Okay, there's K. Is L in the same strongly connected component as K? Yeah, because you can get from K to L and from L to K. What about H? Okay, and so what is the sort of, if you had to circle all the vertices that are in the same strongly connected component with K, what would you circle? All right, this chunk at the bottom here is a strongly connected component of the graph. Okay, we know that D is a strongly connected component of its own, and we know that A is as well. So what are the other strongly connected components? Yeah? So B and E together form a strongly connected component, and C and F. So there they are. Yes. Okay, yeah. G, I, and J are a connected component. But what we're after with strongly connected components are the largest possible chunks. And so these chunks have the property that you can't make them any bigger. And if you put any other vertex in that lower chunk, you won't have a strongly connected component. Yeah. Right. But you can't get from K back to B. Right. It has to go both ways. Now, what if we put an edge from I to A? Right. What if we put a directed edge that went from I to A? How would that change our picture? Well, almost the whole thing would be a strongly connected component, except for D. D would be one chunk, and everything else would be another chunk. Well, C and F would still be, if you had an edge from I to A, you could get from C to, you get from C to A and from A back to C. Right. D would be the only outlier. Now, once you identify strongly connected components, you can start, what we're going to define is what's called a metagraph. So think of those dotted circles as vertices in a metagraph, so meta-vertices. So what we're going to do is ignore the internal structure and just pay attention to how the strongly connected components are interrelated. So now we have a graph with 5 vertices, one for each strongly connected component of the original graph. So this is the first step in producing a metagraph, is just ignore the internal structure. But this isn't quite a graph. Why isn't this really a graph, according to our definition of a graph? Yeah. 2 edges from BE to CF, so you just need to clean that up. Make sure there's just one edge in between it, that connect their vertices. And this is the metagraph for the original graph. All right? And it turns out that it's sometimes very useful to be able to identify a metagraph, which essentially means to be able to identify strongly connected components. And turns out that the metagraph is a DAG. Okay? Why is it? What's the argument that a metagraph has to be a DAG? In other words, has no cycles? Yeah. Right. So if there are two meta vertices involved in a cycle, they need to be one chunk, not two. So it couldn't have. So they would have been one chunk in the original, in the reduced in the metagraph. So you're not going to find cycles. Cycles would collapse into. Like if this had an edge from the GHIJKL up to A, then we know that if we added that edge to the original graph, all but one of the vertices would be the same strongly connected component. You wouldn't be able to derive the structure. Okay. So what I'm going to do is first show you a few examples of how you can make use of strongly connected components, and then we'll look at an algorithm for finding strongly connected components. All right, so first of all, imagine a city that has only one-way streets. So you can model its traffic grid with a graph with the vertices or intersections and its edges or streets. Okay, so to get from this intersection to that intersection, you'd go down the one-way street. So it's a directed edge. Mayer claims that every intersection can be reached from every other intersection, which is a nice property to have, that no matter where you are, you can get anywhere else. What's an efficient way to test this claim? What algorithm would you use to find out if the Mayer is right? Yeah. Right. Find the strongly connected components of the city's graph. And if it's really true that you can get from any point to any other point, you would expect to have only a single strongly connected component. The metagraph should be a single meta vertex. Okay? So that's one example. Here's another one. Okay. The Mayer realizes his first claim wasn't wrong. So what he says now is that if you start driving from City Hall, you will always be able to get back. So how can we test that? Yeah. A topological sort of what? Well, the graph of the city is not a DAG, so we can't really topologically sort it. Yeah? Sure, you use strongly connected components, but what do we do? Let's say we determine the strongly connected components of the city graph. How can we answer the Mayer's question? Yeah. Yeah, there's a simpler way to put it. Yes. Well, you could. The answer to the first question, there would be one chunk. But I'm not asked that question. I'm not saying you can get everywhere from City Hall. I'm saying that wherever you get to from City Hall, you can get back to City Hall. So yes. Well, the metagraph won't have a cycle because metagraphs are acyclic. Wow, lots of hands here. I'll get you. Close. Yeah. Okay, and what's the word for that? Yes. Okay. Well, here's our suppose the Mayer that City Hall is in BE right here. Okay, is the Mayer's claim true? No. You could drive from here down to here, and then you're stuck. So what property are we looking for? Yeah. That's the word. As long as City Hall is located in the sink of the metagraph, then the Mayer's claim is true. So if City Hall is in this chunk here of the metagraph, then in the original graph, no matter where you start from, let's say J is City Hall, no matter where you start from, you can't exit the sink, right? There's no way to get out of it. You end up back in J. Or if City Hall is D, the claim is true. if the city hall is not in a sink, the claim is not true. So the algorithm is, you take the graph, do a compute its strong intent component, and make sure that the meta vertex that contains the city hall vertex original graph is a sink in the meta graph. So we just make sure that the city hall is either in here or in here. No edges out. All right, here's one more example. You remember the price cost problem that we did before, and or maybe not. I'm going to go back and bring it up. Here it is. Okay. So we had this deal where we wanted to compute the cost of the vertex. Every vertex has a price, which is labeled in white. And we want to compute the cost, which I'm going to label in yellow. And remember, what was the cost of a vertex? Like, what is the cost of F? Yeah? Okay, so it's either the larger of the price, which is 2 for F, or the largest cost of anything you can reach from F. And of course, you can't reach anything from F, so its cost is 2. And remember, we just computed this in reverse topological order. Okay, and that works fine if you have a DAG. What if it's a directed graph that's not a DAG? What would be an efficient algorithm for computing the cost? Because this algorithm involves doing a topological sort as the first step. You can't topologically sort an arbitrary directed graph. Yeah. Okay, so the idea is a lot of times, if you need to solve a problem on a directed graph, what you can do is compute the strongly connected components of the original graph, and then run a DAG algorithm on the reduced graph, on the meta graph. Well, let's think how you would do that. Now, this isn't a good example because it's already a DAG. So let's just go back. I shouldn't have closed that just yet. Sorry about that. Okay, let's let this be our graph. Imagine that all these vertices have a price. In fact, we don't really have to imagine. We can do this. Okay, so imagine we gave a price to each of these things. So we give this a 1, a 2, a 4, a 3, a 6, a 2, a 1, a 3, a 7, a 2, and a 1. Okay? What did I just do? Just touch the wire. Okay, and we want to find, those are the prices. We want to find the cost of every vertex. What's the cost of 1? Right? The cost of 1 is going to be the price, basically the price of the vertex that follows with the largest price. So what's that going to be? What's the largest price reachable from A? Down there in J. You can get from A to J. So the cost of A is going to be 7. Okay, but we want to turn this into a problem involving, we know how to solve the problem on the DAG. So let's do the reduction. So here's a meta vertex, here's a meta vertex, here's a meta vertex, here's one, and here's one. Okay, so suppose we did the reduction. We turned that graph, we replaced it with this meta vertex. Now we have to associate a price with each of these meta vertices. Okay, then we can find the cost of each meta vertex. So my idea is we'll associate a price with each meta vertex. Then we'll run our DAG algorithm to get the cost of each meta vertex. And then we somehow have to turn that into the cost of each original vertex. Right? So we reduce, solve the problem, and then translate the problem back. So first question is, what price do we assign to these 5 meta vertices? What do you think? Right, we're going to take the maximum of all the prices that these contain. So we're going to give this one a price of 1, this one a price of 6, this one a price of 4, this one a price of 3, and this one down here a price of 7. Now we go compute the costs using our DAG algorithm. So let's change colors here. Okay, and the DAG algorithm works from the sinks back toward the source. So let's start with the sink down here, the big one. Its price is 7. What's its cost? 7. Okay, now about the one on the upper right. Its price is 4. What's its cost? Okay, the DAG algorithm is just going to, it's going to say, okay, my price is 4, but I can reach a vertex whose cost is 7. So minus 7. Then what about the BE one? 7. And what about A? And what about D? 3. Okay, that's the only one that's not 7. Now, why did it make sense to set the price of every vertex in the strongest net component to the max? Yeah. Well, it's not the matter of lowering number of comparisons. It's a matter of getting the answer right. But what's the right inside a strongest net component? Every vertex can reach every other component. So their cost is going to be at least as big as the highest price contained. So that's why that made sense. Now, once we've done this, how do we turn this back, and how do we translate these white numbers back to the original graph? In other words, what is in the original graph? What should be the cost of G? Right, they would inherit the cost of the meta vertex. So everything in that bottom chart, back in the original graph, is going to have a cost of that. Makes sense because all of them can reach something whose price is 7. Everything, D is going to have a price of 3. Everything else is going to have a cost of 3. Everything else is going to have a cost of 7 because of the way I'm doing this. But that's just another example of taking a directed graph you got to solve a problem on and being clever enough to turn it into a DAG, solve the problem on the DAG, and then translate back to the original. So that's because DAG algorithms are often a lot more straightforward than arbitrary directed graph algorithms. Yeah.
So the operation of the DAG algorithm, would it require
Yes. It would require topological sort of the meta graph. So what you have to do is produce the meta graph, and we'll see the algorithm for that, but it involves doing 2-depth researches in the graph algorithm. So it can be done in linear time. And once you have the DAG, you have to topologically sort the DAG, solve the problem, and then copy the answer back. Yeah. Well, somewhere, when you turn the graph into the meta graph, you've got to have some way of saying what vertices are in each meta vertex. So you would have a list of vertices corresponding to each meta vertex. So you just have to go through that list and look up the price of each one. Yes. Sure. We say, well, it's not a question of going from A to H. The cost of A is 7 because that's the price of the most expensive vertex you can reach from A. You can go cheaper places too, but all right, let's take a break and we'll look at something different. Just 1 second. Okay, so I'm not quite through with strongly connected components, but I'm going to look at the next time when we'll see the algorithm for doing strongly connected components. I want to talk about breadth first search trees in the time that's left. So we have been studying depth-first search and its applications. But when we do depth-first search, it's not like we're searching for something. You don't typically use depth-first search to find paths in a graph. Why do you do depth-first searches? Yeah. For topological sorting, for example. We use it to gather information about the graph for other purposes, such as topologically sorting it, or turning it into strongly connected components. Yeah. Right. Depth-first search will find a path if one exists. But you may notice that when our depth-first search algorithm did not record enough information to produce a path, right? As we did the depth-first search, we weren't remembering what vertices we took anywhere so that we could reconstruct a path. You could in principle, but typically you're not doing a depth-first search for that reason. So in fact, depth-first search in the book, it comes in a chapter called graph decomposition. Breadth-first search, on the other hand, comes in a chapter called graph search. So with breadth-first search, we're doing it not to get pre and post numbers. We're doing it because we're interested in finding paths. So the data structure we use looks a little bit different. So let's think about breadth-first search trees. So a breadth-first search begins at a specific vertex and finds the shortest path to every other vertex. And if there are some vertices that you can't get to, you just can't get to them. Depth-first search, if we couldn't get to a vertex, we started over. We restarted the search at a vertex we couldn't reach and gradually visit everything. But with breadth-first search, you just stop when you've reached everything that you can. So let's think about the shortest paths from A to every other vertex. Okay, so that's the shortest path from A to B, right? There's no shorter way. That's the shortest path from A to C. There's no other way. What would be the shortest path from A to D? We can either go A, B, D, or A, C, D. So let's just say we do A, B, D. And what's the shortest path from A to E? Yeah? A, B, D, E is link 3. What's another one? Oh, A, C, D, E. So let's suppose we do that one. So I've sort of encoded the information in colors. And so we see that we've got the green path from A to D, the yellow one from A to B, and so on. Now, what if you, at this point, threw away the unused white edge and then merge all the colored edges, like the yellow, we've got 2 edges from A to B, replace it with 1 edge. We've got 2 edges from A to C, replace it with 1 edge. What do we have left? You just combine some of the colored edges and get rid of the white edge. You've got a DAG, a breadth-first search DAG. Okay, we don't want a breadth-first search DAG. We would like an algorithm that produces a breadth-first search tree. And I'll show you what I mean. So this note says all the paths taken together do not form a tree, because there are 2 ways. Following a colored edge, you can get from A to D in 2 ways. So it doesn't form a tree. But it's always possible, though, to find a tree, a breadth-first search tree. So let's do that here. Now, I think my graphs are messed up. We go from A to B like before. We go from A to C like before. We go from A to B. So the white edge from B to D is missing. I don't know why. It's like these things rot over the summer. Okay. So instead, before we went from A to D from A to E by going A, C, D, E. What'd be the better way? Right. Go that way. If you go that direction, you end up with a tree. If you just get rid of the white edges and combine the colored edges, you get a tree shape. So we've got to make sure that our algorithm produces a tree when it does its breadth-first search, that the edges that it uses form a tree, not a DAG like above. Okay, so there's that picture there, and this is what I'm talking about. If you just combine the colored edges into purple edges and ignore the white edges, you've got a tree superimposed on the graph. Breadth-first search. And this is why we want to have a tree. we want to be able to encode the tree into two arrays. So the output of our breadth first search algorithm is going to be these two arrays right here, previous and distance. And previous is going to be the parent of the vertex in the breadth first search tree. So we started at A, so it has no previous. Why is previous of B the A vertex? This right here is our breadth first search tree. So why is the previous of B A? Yeah? Right, in this tree, there's a purple edge from A to B. Okay? Why is previous of C going to be A? Same reason. Previous of D is going to be B, and the previous of E is going to be D. Now, why was it important that we have a breadth first search tree instead of a breadth first search DAG? Yeah. This wouldn't work. If the depth first search DAG also had a purple edge from C to D, if you had that possibility, what would be previous of D? It would be B and C. But as long as you've got a breadth first search tree, then there's only one parent in the tree. Yeah. Well, A star is you're using weighted graphs, right? So we're talking about shortest paths in unweighted graphs. The edges don't have weights. We'll eventually look at algorithms that use where you put weights on the edges, and there the notion of shortest paths means something different. Now, the distance array, what does it encode? Right, how far it is from A. So A is 0 edges from itself in the tree. B is 1 edge away. C is 1 edge away, and so on. So to get from A to E in the tree, 3 edges. Furthermore, if we just go back to the original graph, this distance is the minimum number of edges you have to follow to get from A to E. So it's the length of the shortest path from A to every other vertex is encoded in the distance array, where we count distance in terms of number of edges traversed. So we need an algorithm that takes a graph and produces those two vertices. And that's our breadth first search algorithm. Now, what if we had an F right there? How would it be coded? What would the previous of F be? It wouldn't have a previous, and what would its distance from A be? Yeah, so we have to mark it somehow. So we'll say F has no parent, it has an infinite distance. And so looking at this, you can tell what the start vertex was, because it's the only one with a distance of 0. And you can tell what the unreachable ones are, because they have distances of infinity. Everything else is reachable. All right, so here's my algorithm. What I'm going to do is I'm going to have my distance array and my previous array. So I'm going to initialize everything in the distance array to infinity and everything in the previous array to null. And then to set things off, I'm going to set the distance of S to 0. Now, what's S? Right, so breadth first search takes two parameters, the graph to search and the starting vertex. So depth first search, there was no starting vertex. You just sort of picked one arbitrarily. But in breadth first search, there's definitely a starting vertex. So we set the distance of S to 0. Then we create a queue, and we stick S on the queue. So there's down here, which is covered up now by that box, is where I'm going to put the queue. And then we enter the loop. So let's work through the algorithm and just see how it operates. So what we're going to start by doing is I'm going to execute that code, and it's going to set my arrays to that state right there. All the previouses are null. All the distances are infinity except for A, which is the start vertex. And then we're going to create a queue and put A on it. So there, A shows up on the queue. And now we just write a loop that each time through the loop, it pulls something off the queue and does something with it. So let's see how it works. So first thing we're going to do is the queue is not empty, so we're going to pull A off the queue. And I'm going to color it yellow when it comes off the Q. So if a vertex is on the Q, I'm going to keep it purple so you can see that it's on the Q. When it comes off the Q, I'm going to color it yellow. Now, what's the next thing we do? So U is, at this point, is A. So what does this code here say to do? Okay, so it's looking for every adjacent vertex. In other words, every vertex you can reach with one edge, which is what? What vertices can we reach? B, E, and F are reachable in one step. If their distance is infinity, what's special about infinity? Well, it's greater than every number, but what does it signify if someone's distance is infinity? Yeah. Right, we haven't seen that. It's a vertex we haven't seen before. Because what we immediately do when we see a vertex that we haven't seen before is we add to the Q, we set its distance to something, and we set its previous to something. So its distance is no longer going to be infinite once we've seen it. So we follow that edge, we see the B, it goes on the Q, and what else happened? I'll back up and do it again. What's changing in the array up there? Right, previous is A, because right now we're in that loop, U is A. So we remember we got there from U, and why is its distance 1? The distance to V, which is B, is 1 more than the distance to A, which is 0. Okay, so let's just continue. Now we look at E, and the same thing happens. E gets thrown on the Q, and the array gets updated for E, and the same thing for F. And then we're done with the loop. Now, at this point, everything on the Q are the things we could reach in one step from A. Now, does it matter which order B, E, and F went on? Could we have put them on F, E, B, or E, B, F? Yeah, doesn't matter, as long as we do with them all. But now we're going to take the first item in the Q off, which is B, so B becomes our new focus. And we repeat the process. We look at that edge. We have not seen C before, but what is previous of C going to be? B. And what is distance of C going to be? 2, because it takes 2 hops to get from A to C. But why? How do we compute the 2? It's 1 more than the distance of B is. We know B is 1 hop from the root, so C must be 1 more than that. So that goes on the Q. We check out F, and what happened? Right, it has a non-infinite distance, so we ignore it. So now look at the Q. Some of the elements on the Q have a distance 1 from A, and some of them have a distance 2 from A. Well, what properties does the Q have at this point? Yeah. No, I guess that's true, but kind of misleading because this isn't a DAG, is it? There's a cycle in there, and so it really doesn't have to do with reachability. There's a more important invariant with the Q. Right. The thing to realize is essentially the Q is sorted. The things on the left have the smaller distances. The things on the right have the larger distances. And that's important because that means that we're going to DQ the things that are closer to A first. So why would it be wrong to DQ C first? How would things go awry? Or how could things go awry? Or I guess in this situation they can't. I'll have to make this point later. So hold on. So let's pull E off the Q. And what will happen? We're going to check it. We've already been to F. And there's no other edges out of E. So what will happen next is we'll pull F off the Q. And we're going to look at C. And we've already been there, so there's nothing to do. And then C comes off. So we visit everything out of A first, and then we visit everything out of vertices that are 1 hop away from A next. So we're advancing the fringe of the tree, steadily staying with the close vertices first. That's what makes it breadth first. So now we're on to things that are 2 hops away. So what's going to happen with C? All right, it has the 2 edges. So B will get a distance of 3, and G will get a distance of 3. And that's all the edges. So D comes off next. And it tries to visit H. It succeeds. It gets a distance of 4. There are no other edges. G tries to visit H. It's been visited. And we never even get to see I. So it just gets left with infinite and slash. So it's important that we use a queue. If we use a stack, what would we be getting? Yeah. It'd be something close to depth first search. The reason it's not exactly depth first search would be with a stack, you'd have to be careful. You have to be really clever when using a stack that you get the pre and post numbers correct. With recursion, it's quite natural. If you use a loop and a stack, you can still do depth first search, but you gotta think pretty hard about the pre and the post numbers. So that's breadth first search, which finds what we have found is the shortest path from A to every other vertex. Now, I say we found the shortest path. How would you recover from this, the shortest path from A to H? Because this doesn't store paths, it just stores edges, yeah. Okay, you trace the previous from H all the way back. So you start at H, and its previous is D, and D's previous is C, and C's previous is B, and B's is A, and A is the root. So that gives you the path in reverse. You start at the destination, you can work back. So that's the beauty of that nice encoding right there. It's just a couple of lists, a couple of arrays, but it encodes all the shortest paths. Now we can quickly analyze this because it's about the same as depth first search. So let's do that. The cost of that initialization loop is O of V, right? We're filling in 2 arrays of size V. What's the cost of creating an empty queue? No, it's just constant time. Think of it as a linked list, an empty linked list to start with. And then we have to enqueue S. What's the cost of that? That's constant. Then we got to test if the queue is empty over and over again. How many times do we test if the queue is empty? Once per vertex, right? At most, that loop is going to go around once for each vertex. So, and the test itself is constant, so that's an O of V test. How many times are we going to pull something off the queue? That's V times again, and each pull is constant. Then we've got to, over the life of that while loop, we've got to find all the edges in the graph. And that depends how the graph is represented. So I'm just going to call that whatever that is. It's the cost of enumerating all the edges out of a particular graph. How many times are we going to test to see if a vertex has been visited? In other words, how often do we do that if distance of V is infinity? Yeah, at most 1 per edge, right? We ended up looking at every edge in the graph. So that test is going to be O of E. You can do that once per edge. And then we've got to do an enqueue, which is constant time, and those 2 array operations, which are constant time. But how many times will we do that? How many times does a vertex get enqueued? Once. So we're going to do each of those operations once for each vertex at most. That's O of V. You add it all up, you get that. And for matrix, what's that going to reduce to? Right. It's O of V plus O of E plus O of V squared, which is O of V squared. And for the list, it's that, which is that. But it's linear again. So depth first search is linear the same way that, breadth first is linear the same way as depth first search. So efficient algorithm. And this is a good stopping point because that's breadth first search. That leads us to what happens when you put weights on the edges. Game changes.